Hi, welcome to Bad Statistics in the News, the CDC guidelines on COVID-19 antibody tests and how CNN reported them. Statistically imprecise or wrong statements are unfortunately common in news reporting. This video is about an example of this phenomenon that recently popped up regarding antibody tests for COVID-19. The Centers for Disease Control and Prevention, or CDC, recently put out guidelines on antibody tests for COVID-19. If you want to look at the guidelines, you can look at a link in the description. They include a couple of simple examples on how false positive and false negative rates of these tests affect the probability that a person who tests positive for the antibodies actually, in fact, has the antibodies. CNN covered these guidelines in a story entitled Antibody Tests for COVID-19 Wrong Up to Half the Time, CDC says. And if you'd like to read that article, the link is given in the description. Now, the examples given in the CDC guidelines were statistically sound, but some of CNN's conclusions drawn from the examples in the CDC guidelines were not. Here, we'll go through the two examples in the CDC guidelines. Then we'll look at how CNN covered them and how some of their conclusions don't follow from the examples in the CDC guidelines. So, antibody tests can potentially tell us if a person previously had COVID-19. One reason this is important concerns the possibility that those who have had COVID-19 in the past may be immune to reinfection. Right now, there is a lot that is not known about possible immunity to COVID-19. But if at some point we find that people who have COVID-19 antibodies have some immunity to reinfection, we would want to be able to know if a person is protected or still susceptible to the illness. Now, COVID-19 antibody tests, like all medical tests, have non-zero false positive and false negative rates. So here, a false positive is when a person with no antibodies tests positive for the antibodies, and a false negative is when a person with antibodies tests negative for the antibodies. Now, this complicates how one should interpret the results of an antibody test. We don't want someone to believe that they have protection against COVID-19 infection if they actually do not. And we don't want a population to think herd immunity has been achieved when it has not. Either of these could lead to a dangerous false sense of security. So this means that a really important question that we should ask is the following. If someone tests positive for COVID-19 antibodies, what is the probability that they actually do have COVID-19 antibodies? The CDC gave a couple of simple examples to show how false positive and false negative rates affect the answer to this question. They also give more general information about antibody testing, but we'll focus on their statistical examples. Okay, so let's start with example 1. Here we have the following hypothetical scenario. So, first of all, we're going to take the prevalence of COVID-19 antibodies in the population as 5%. So what this means is that 5% of people in the population truly do have the antibodies. We're also going to assume that we have a test for COVID-19 antibodies. And we're going to say that the test has a false negative rate of 10%. So this means that of people who have the antibodies, 90% correctly test positive, but 10% incorrectly test negative. Additionally, the test has a false positive rate of 5%. So this means that of people who do not have the antibodies, 95% of them will correctly test negative for the antibodies, but 5% will incorrectly test positive for the antibodies. Okay, so now let's reiterate that question that we want to answer. If someone tests positive for COVID-19 antibodies, what is the probability that they actually do have COVID-19 antibodies? We'll imagine we have a sample of 10,000 people and ask what we'll see in this sample on average. Okay, so we have a sample of 10,000 people, and the prevalence is 5%. So this means on average, 5% of those 10,000 people, or 500 people, will truly have the antibodies. 95% of the people, or 9,500, will not have the antibodies. Now we have a false negative rate of 10%. This means of the 500 people who truly have the antibodies, 10% of them, or 50, will incorrectly test negative. The other 90%, or 450 people, will correctly test positive. Additionally, we have a false positive rate of 5%. So out of the 9,500 people who do not have the antibodies, 5%, or 475 of them, will incorrectly test positive. The other 95% of them, or 9,025 people, will correctly test negative. This tells us that we will have a total of 925 positive tests and a total of 9,075 negative tests. Now let's just briefly remind ourselves of which of these test results are correct and which are incorrect. So the correct test results are for the people who have the antibodies and test positive, and for the people who do not have antibodies and test negative. The people who have antibodies and test negative, and the people who do not have antibodies but test positive, get incorrect results. So now we can ask what fraction of positive tests actually gave correct results, and what fraction of negative tests actually gave correct results. So we can divide the number of correct positive tests, which is 450, by the total number of positive tests, which is 925. And we can divide the number of correct negative tests, which is 9,025, by the total number of negative tests, which is 9,075. This tells us that 48.6% of people with positive test results get an accurate result, and 99.4% of people with negative test results get accurate results. So a person who tests positive has only a 48.6% chance of actually having the antibodies. We can also ask what fraction of people who truly have the antibodies get accurate test results. That's 90%. And we can ask what fraction of people who truly do not have the antibodies get correct test results, and that's 95%. This latter set of numbers is closely related to our false negative rate, which was 10%, and the false positive rate, which was 5%. Okay, so now let's look at that number 48.6%. Why is this number so low? So remember that the prevalence is very low, only 5%. Very few people truly have the antibodies, so there can only be so many correct positive test results. But there are so many people without antibodies that even though there is a small false positive rate, that small false positive rate gets multiplied by a large number of people who do not have the antibodies. This gives us a non-negligible number of false positive test results. Okay, now let's go to the CDC's second example. So again, we have a hypothetical scenario. Here, the prevalence of COVID-19 antibodies in the population is 52%. The test has the same false positive, that's 5%, and false negative rates, that's 10%, as before. And note that the prevalence is the only thing that has changed relative to example 1. So again, we have a sample of 10,000 people, but this time the prevalence is 52%. So that means that 5,200 of them truly do have the antibodies, while 4,800 of them do not have the antibodies. Now, again, we have a false negative rate of 10%. This means that of the 5,200 that truly have the antibodies, 10% of them, or 520, will test negative. The other 90%, or 4,680, will correctly test positive. We also have a false positive rate of 5%. So this means of the 4,800 that do not have antibodies, 5% of them, or 240, will incorrectly test positive, while the other 95%, or 4,560, will correctly test negative. So again, we can ask what fraction of the positive tests are correct and what fraction of the negative tests are correct. So again, we can divide the number of correct positive tests, which was 4,680, by the total number of positive tests, which is 4,680 plus 240, which is 4,920. And we can divide the number of correct negative tests, which was 4,560, by the total number of negative tests, which was 5,080. And this time we get that of the people who test positive, 95.1% of them do receive a correct test result, while of those who test negative, 89.8% of them receive a correct test result. Now, these results of 95.1% and 89.8% might seem a bit more intuitive than the results that we got for example 1. In this case, 95.1% of people who test positive for the antibodies really do have the antibodies. So here, the prevalence is around 50%. So this means that the numbers of people with and without antibodies are comparable. So this time we no longer have an overwhelming number of people without antibodies being multiplied by the false positive rate. It's important to keep in mind, however, that in these two examples, the tests were exactly the same. The difference in the results from the two cases was due to the difference in the prevalence of antibodies in the population. If the prevalence is small, the positive tests can be dominated by the false positives of the overwhelmingly larger number of people who do not have the antibodies. The CDC suggests strategies such as using antibody tests only in cases where the prevalence is not too small, or retesting people who test positive with a second antibody test. Okay, so now let's look at how CNN covered these guidelines. To look at the CNN story, we need to go back to example 1. Okay, so the CNN story zeroed in on this number of 48.6%. So again, this was the fraction of people who received a positive test who in fact were positive for the antibodies. So they concluded from this that the antibody tests can be wrong up to half of the time. It is true in this example that the positive results are correct only about half of the time. But the positive results make up only a small fraction of the total. Most of the tests come back negative, and the vast majority of them give correct results. Overall, in this example, the test was right 94.75% of the time. To better see why CNN's description of the tests is not reasonable, let's make up a slightly pathological example. Let's say there's a disease called Martian foot disease. We have a really good test for it that has false positive and false negative rates of 0.01%. Let's say we have a population where the prevalence of Martian foot disease is 0. Nobody has it. Let's see what would happen on average in a sample from this population that contained 1 million people. Okay, so again, we have 1 million people, but the prevalence of Martian foot disease is 0. So this means out of the 1 million people, 0 of them have Martian foot disease, and 1 million of them do not have Martian foot disease. Now, we have a false negative rate of 0.01%. However, we have no people in the sample who are actually positive for the disease. So 0 times 0.01% is 0. We do, however, have a false positive rate of 0.01%. And we have 1 million people who do not have Martian foot disease. So 1 million people times 0.01% is 100. So we do get 100 people who test positive. And out of these 100 people who test positive, 0 of them get a correct result. So none of the positive tests are right. All of them are false positives. But it would be ludicrous to say that the test can be up to 100% wrong. It got 99.99% of the results correct. And additionally, it would get 99.99% of results correct even if the prevalence was non-zero. In fact, even if the prevalence was large. This is a highly accurate test, but just looking at the positive results won't tell you that. Now, it is true that in example 1, a person who tests positive has a large uncertainty as to whether or not they really carry the antibodies. If a person tests positive, the probability they actually carry the antibodies depends on the prevalence. It cannot be obtained from the false positive rate alone. This is an important point that should be reported. But this result should not be taken to represent the behavior of the test as a whole. As our pathological example shows, if we choose a case where the prevalence is very, very low, we can make even an excellent test look bad if we only look at a subset of the test results. The CNN story could have represented the CDC example much more accurately with a simple change. Instead of saying that the antibody tests can be wrong up to half the time, they could have stated that the positive results from antibody tests can be wrong up to half the time. This would be a major improvement. There were also a couple of other issues with the CNN story. First, it should be pointed out that the false positive and false negative rates and the prevalence used in the CDC examples were hypothetical examples. These rates may or may not be reflective of reality, but the CNN headline, "Antibody tests for COVID-19 wrong up to half the time," CDC says, most definitely did not make this clear. In fact, if the CDC examples had used a 1% prevalence, the positive test results would have been right even less often. Lastly, there was one more statistical issue with the CNN story. The CNN story states that if the prevalence is just 5%, a test with more than 90% accuracy can still miss half of cases. While one can arrange such a scenario, this is not what was happening in the CDC examples. So, missing half of cases does not correspond to half of the people who test positive not being true positives. Instead, missing half of the cases corresponds to half of the people who have antibodies getting negative test results. That's not what was happening in the CDC examples. Okay, so now let's briefly summarize. What we've seen here is an example of statistics not being treated properly in news reporting. This is all too common, but it's a good example of why it's important to understand statistics. If you don't, it's very easy to come to very wrong conclusions. Very wrong conclusions about possibly very important matters. And lastly, understanding the results of medical tests is actually a classic example of Bayesian reasoning. There are 2 videos on this channel that deal with this issue directly. The first of them is called Bayesian Logic at the Vet, a brain teaser. and the second of them is called Medical Tests, Bayes Theorem, and How a First Guess Can Lead to an Absurdity. You may also be interested in other videos in the Bayesian playlist.